Welcome to The Explainer. Today we are going on an absolutely incredible journey, tracing how we as humans have figured out our place in the universe. And let me tell you, it's a story all about shattering our most deeply held beliefs in a relentless search for what's real. For, well, most of human history, the answer to this question was a resounding yes. The geocentric model, with the Earth right in the middle of everything, that was our reality. But the story of science is really the story of asking the tough questions and having the guts to accept the answers, even if they knock us right off our pedestal. So our journey has to begin with that first, gigantic paradigm shift, the one where we dethroned Earth, a move that would completely rewrite our entire frame of reference. On the one hand, you had the classic geocentric model. It worked pretty well from our point of view here on Earth. But then, in 1543, Nicolaus Copernicus comes along and suggests something pretty radical, the heliocentric model, with the sun at the center. It was just cleaner. It explained a lot of nagging problems, like why the planets sometimes look like they're moving backwards in the sky. Okay, but a brilliant idea is one thing. You need actual proof. And that's where Galileo Galilei comes in. In 1610, he points his brand new telescope up at the sky. First, he sees moons orbiting Jupiter. Wait a minute, things not orbiting Earth? Then he sees that Venus has phases, just like our moon, something that was totally impossible in the old Earth-centered model. For the first time, what we could see was challenging what we had believed for centuries. So, now we know our place, we're in orbit, great. But the next huge question was, just how big is this place? How far away are all those little lights in the night sky, really? The key to unlocking this was a concept called stellar parallax. The idea itself is actually pretty simple. As the Earth swings from one side of its orbit to the other, a star that's relatively close to us should seem to shift its position just a tiny bit against the very distant stars. The problem? For centuries, this shift was just too small to measure, which actually led some really smart people to argue that the Earth couldn't be moving. The method is basically just 4 steps, and it's all about simple trigonometry. You look at a star, you note its position, then you wait 6 months until the Earth is on the complete opposite side of the sun, and you look again. That tiny little wobble you can now measure tells you exactly how far away it is. This, right here, is the very first rung on what astronomers call the cosmic distance ladder, our way of measuring the sheer vastness of space. After so many failed attempts over hundreds of years, it finally happened in 1838. Friedrich Bessel actually did it. He measured the parallax for a star called 61 Cygni and proved it was trillions upon trillions of miles away. This one measurement just blew the roof off the old ideas and turned the universe from a cozy celestial dome into a 3-dimensional space of almost terrifying depth. Okay, so we've got a sense of scale. The universe is huge, but it was about to reveal its most dynamic secret of all. It wasn't just sitting there. It was growing. The 20th century just lit the fuse on discovery. In the 1920s, Edwin Hubble figured out that those fuzzy nebulae in the sky, like Andromeda, weren't in our galaxy at all. They were entire other galaxies, island universes far outside our own. And then he dropped the real bombshell. Almost all of them are rushing away from us. The universe itself was expanding. Now think about that. If the universe is expanding, what happens if you run the movie backwards? Everything must have been closer together, right? Well, a physicist and priest named Georges Lemaitre put it all together and proposed that the universe began as a single primeval atom, a super hot, super dense starting point. We'd later call it the Big Bang. And the final proof for this crazy idea came, of all things, by total accident. In 1965, 2 astronomers, Arno Penzias and Robert Wilson, kept picking up this annoying, persistent hiss in their radio antenna no matter where they pointed it. It wasn't equipment noise, it was the cosmic microwave background, the leftover heat, the literal afterglow from the creation of the universe. So the picture is getting clearer, but this is where the story gets really, really strange. It turns out the main characters in the story of our cosmos are things we can't even see. Okay, so based on all of our laws of gravity, this should be simple. In our solar system, the outer planets move slower than the inner ones. So in a galaxy, the stars on the outskirts should be moving way slower than the stars near the center, where all the bright, visible stuff is. Makes sense, right? Well, in the 1970s, Vera Rubin's incredible observations showed that this just wasn't happening. Her data was clear. The stars way out on the edge of galaxies were moving just as fast as the stars in the middle. The numbers just didn't work. Unless there was a whole bunch of invisible matter, a hidden mass providing extra gravity. And that something else got a name: dark matter. You can't see it, it doesn't interact with light, but it's the invisible gravitational glue that holds galaxies and really the entire cosmic web together. And just when you thought it couldn't get any weirder, it did. In 1998, scientists were using exploding stars, these supernovas, as cosmic mile markers. They were trying to measure by how much the universe's expansion was slowing down due to gravity. But they found the exact opposite. The expansion isn't slowing down at all. It's speeding up. And the results of all this is, well, it's this. This chart is just mind-blowing. All the stars, all the planets, you, me, everything we've ever seen or touched makes up only about 5% of the universe. The rest is the stuff we don't understand. Dark matter, holding it all together, and something we call dark energy, pushing it all apart. And that brings us to today. Our standard model of cosmology is amazingly successful, but it's also fundamentally broken. It's built on two giant mysteries that make up 95% of everything. So, naturally, the search is on for a new, more complete physics to explain it all. One of these proposals is a whole new framework called Realica Cosmology. And its goal isn't just to patch up the old model, but to rebuild our understanding of the universe from the ground up with a totally new foundational physics. One that tries to explain everything without needing any mysterious, unknown stuff. So this new model looks at the big problems differently. Where the standard model says we need some kind of exotic dark matter particle for that extra gravity, Realica suggests that the gravity is coming from the very structure of space-time itself. And that dark energy? It suggests that the accelerating expansion is just a natural property of an oscillating vacuum. What you get is a complete model that doesn't start with an unknowable, infinitely dense point, but with a stable, oscillating state. And here is the most important part. It makes a clear, testable prediction. It says we should be able to find a fundamental spectral line at a very specific frequency, 114.11 terahertz. This gives physicists a target they can actually look for to see if this whole idea is right or wrong. So we've gone from believing we were the absolute center of it all to realizing we're made of just a tiny 5% sliver of what's really out there. With every step on this journey, the universe has gotten bigger, stranger, and our own place in it more humble. The search for coherence goes on, and it just reminds us that the biggest discoveries might still be waiting for us right around the corner.